This is a short video just to look at one of the key techniques in the differentiation topic in higher mathematics. That technique is sketching curves. When curve sketching, there are four things that we need to find. We need to find the y-intercept, where the curve intersects with the y-axis by setting x equal to 0. We need to find the x-intercepts, so we set y equal to 0 and we solve, and that will often involve factorising. We also then crucially need to find the stationary points. This is quite often the bulk of the work. We find the stationary points and the nature of those stationary points, whether they be maximums, minimums, or points of inflection. And finally, and more difficult for some pupils, the behaviour of the curve as x approaches very small values or very big values. So let's look at an example. Example 1, this is drawn from exercise 6n in the Heinemann Higher book, and it's one of those questions. Sketch the curve y equals x bracket x minus 3 all squared. So we notice that this has been factorised for us, which is useful. We have to find the y-intercept first of all, so we set x equal to 0. And doing that, of course, is very simple. We find that y also equals 0. So our first point on this curve is 0, 0. Notice also that this being an intercept on the y-axis, it's also an intercept on the x-axis. I've put a box around the point because I want to make sure that I'm clear that that will be one of the points that I have to graph later. We also need to find the x-intercepts. We do that by setting y equal to 0 and solving. So now we have x bracket x minus 3 all squared equals 0. This has been factorised already. That makes it easy. We've got x equals 0 or x equals 3, a repeated root. So the 2 points are 0, 0 and 3, 0. So we have our intercepts on the axes. Now we look at the stationary points. To find stationary points, we have to find solutions to f dash x equals 0. Now this function was already factorised, so we have to break that bracket and return it to its original form ready for differentiation. So we simply do that, and then we now can find dy by dx. That'll be 3x squared minus 12x plus 9. Remember, you can pause the video at any point just to follow the steps that I'm going through. We set that equal to 0, we divide through by 3, and we factorise, giving us two stationary values at x equals 1 and x equals 3. Of course, these are just the x-coordinates. We need the actual point, so we need the y-coordinates that go along with these. So now I'm going to find the y-coordinates. At x equals 1, we find that y equals 1 times 1 minus 3 all squared, which is just 4. So the point 1, 4 is a turning point, and at x equals 3, we get 0. 3, 0. In fact, this was one of our x-intercepts earlier on. So it turns out this point is a turning point that's on the x-axis, and that sometimes happens. For each stationary value, we need a nature table. And this is very important that we set this out carefully. We need two distinct nature tables for each of the stationary values. And we start with x, then we have dy by dx, and then the shape of the curve. And it's useful to put the derivative in factorised form on the left-hand side. So remember, this was the derivative here, but in factorised form, it looked like this. So I'm going to put that alongside my nature table so that I don't have to keep looking back at it. Station value of 1, we want something before 1, we'll go for 0, and something after, we'll go for 2. When x equals 1, we know that dy by dx is 0, the graph is stationary. When x is 0, if we put 0 into this, we'll have minus 1 times minus 3, that's a negative times a negative, positive. So it'll be rising, the curve is rising. If we put 2 in here, this will be positive, but this will be negative. So we end up with a negative, so that's falling. So we've got a maximum, 1, 4 is a maximum turning point. Again, similarly for the stationary value at x equals 3, we can find something before, we can actually repeat the use of 2, and then we can do 4. And we find that this is a minimum turning point. 3, 0 is a minimum turning point. So we now have our turning points and our intercepts. We're ready actually to sketch the curve, but we need to do just one more thing. We need to think about what's happening as x is approaching negative infinity or positive infinity. So as x approaches negative infinity, it gets smaller and smaller and smaller. What happens to this value, this y value? Will it be very big or very small? So this will be a really big negative number here and a really big negative number here. This whole thing is squared, meaning that it will be positive and very big, but this will be negative and very big. So the whole thing is actually negative and very big. So we've got, as x approaches very large negative values, the y also approaches large negative values. What that means actually is that as we move along the x-axis this way, the curve is going that way. So that just tells me it's coming from down here on its way up. Similarly, we can look at x approaching very big values. So we've got x very large and very large here. So overall, actually, this will be very large. So it's just y approaches infinity. So we need to do that step just to show that we understand what's happening at these two endpoints. But ultimately, we're ready to draw the graph. We can now look back to the points that we need to plot. We need to plot 0, 0 and 3, 0. 0, 0 and 3, 0. These are intercepts. We need to plot the turning point 1, 4 and 3, 0. 1, 4 was a maximum, 3, 0 was a minimum. That gives me the basic sketch of the curve. And that completes this example, and I'll now look at example 2 in the next video.